Hello, this is Dr. Hanaa Assil, and this is Unit 5 of January 2023. This is in the Pearson Edexcel International A level. So let's take a look at the questions and discuss the answers. The first question says, in which species does the transition metal have the lowest oxidation number? So let's take a look at the oxidation number of each transition metal and choose which one is the lowest. So if we say copper with ammonia and overall there is one positive charge, you know that the ammonia itself does not have a charge on it, and that means the +1 is the oxidation number of copper. So in this case, copper has an oxidation number of +1. I'm just going to remind you that oxidation number just means the charge on the ion. So in Fe cyanide 6, overall 3-. You should know that each cyanide has a negative charge. So that means I have 6 negative charges. If the overall is 3-, that means that the ion was 3+ or +3. Manganese sulfate, you should know that the valency of sulfate is 2, so this is 2-, so manganese is +2 since there is no overall charge. Nickel with 4 CO. Now, each CO is has no charge, so the nickel has no charge. So the nickel here has a charge on oxidation number of 0, and that means that is the one with the lowest oxidation number. A complex ion of chromium 3 has this formula where X is the overall charge. What is the coordination number of chromium 3 in this complex ion? Of course, the coordination number is just the number of coordinate bonds or the number of bonds to the ligand. So we have 2 chlorines and we have 2 of this NH2, CH2, CH2, NH2. So this is something that has 2 NH2s, and that means each one of it will make 2 bonds with the chromium, and that means I have an overall of 6 bonds to these ligands. So this coordination number is 6. What is the overall charge on this complex ion? So this was the complex ion. He already tells me anyway that the chromium was +3 or 3+. You should know each chloride is a negative, and that means I have 3+ and 2 minuses. I have an overall charge of +1. Which complex ion is colorless? You should know that the ones that are transition would have a color. The one that is colorless is the one that is not a transition metal. So in this case, aluminium, any complex ion with aluminium would not be colored, would not have a color because aluminium is not a transition metal. But copper complex here is blue. The iron complex here is brown. This is iron 3+, and the nickel 2+ is a green color. So the one that has no color is the complex with aluminium. Which metal hydroxide precipitate is soluble in both excess aqueous ammonia and excess aqueous sodium hydroxide? You should know that, for example, copper. If I put copper ions in excess ammonia, the precipitate which would form, which would be a blue precipitate, would dissolve in excess ammonia, but it would not dissolve in excess sodium hydroxide. If you add sodium hydroxide to a copper ion, it gives blue precipitate insoluble in excess. Now, iron, this is iron 2. Iron 2 will form a green precipitate that is not soluble in excess ammonia, and it's not soluble in excess sodium hydroxide. So it's insoluble in both. Now, what about the nickel? The nickel ions, when we put aqueous ammonia, it would form a precipitate that is soluble, but with aqueous sodium hydroxide, it would not, the precipitate would not dissolve. He wants something in which the precipitate will dissolve in both. Well, zinc precipitate dissolves in both. Remember, if we add aqueous ammonia to zinc ions, it forms white precipitate, soluble in excess, giving colorless solution, and the same with sodium hydroxide. The formula of hydrated copper 2 bromide is this. What is the percentage by mass of water of crystallization in this compound? Okay, in order to get the percentage by mass, I have to get the overall MR for it. So that is mass of copper plus 2 bromines plus 4 of the water, and the overall MR is this. Now he wants the percentage of water of crystallization. How much water do I have in this? I have 4 times 18 over the total times 100. This gives me my percent water of crystallization. The diagram shows how the relative color intensity of an aqueous solution containing 0.001 mole of chromium-3 ions varies with increasing amounts of cyanide. Now, he's telling me that chromium-3 also forms a complex ion with EDTA with a greater relative color intensity. Now, what is EDTA? This is EDTA. It is a ligand that is hexadentate. So it forms 6 coordinate bonds with the central ion. So that means I have 1 chromium bonding with 1 EDTA. It's a 1-to-1 ratio. While the cyanide, remember that if I have it bonding with the cyanide, it has 6 cyanides for each chromium. And that means if we have 0.001 mole of chromium-3 ions, it will need 0.006 of the cyanide. And that's why the graph shows a peak at 0.006 moles of ligand. Now, when we're doing EDTA, he's telling me with EDTA, first of all, we have a greater relative color with EDTA. And that means if I look at that graph for the cyanide, it is going up to relative color intensity of 6. With the EDTA, it should go above 6 because he's saying it's a greater relative color intensity than the complex ion formed with cyanide ions. So he has diagrams and he's telling me which diagram shows the change in relative color intensity when increasing amounts of EDTA are added to an aqueous solution, again containing 0.001 mole. Remember, the graph that we had was for cyanide. That graph up there is for cyanide. And we said for each chromium, we have 6 cyanides. So for the 0.001 mole of chromium-3 ions, it needs a peak at 0.006. But for EDTA, which one of these would apply to the EDTA? First of all, he said the relative color intensity with the EDTA should be higher. So it's either C or D. And then, is it higher at 0.001 or is it higher at, what is that, 0.003? We said it is a 1-to-1 ratio with EDTA because EDTA is a hexadentate. So just 1 molecule of EDTA will make 6 bonds with the chromium ion. Persulfate ions react slowly with iodide ions at room temperature unless a catalyst of ion 2 or ion 3 is added to the reaction mixture. Which of these is the most likely reason why this reaction is slow without a catalyst? So he's telling me that if I add a catalyst, the reaction would be faster. Why is that? Is it because the E cell is positive? Well, that wouldn't be the answer because if the E cell is positive, anyway, the reaction would be fast without a catalyst. Delta H is positive. Well, that also is not affected by presence or absence of the catalyst. Delta S total is positive. If the delta S total is positive, the reaction would be fast on its own without a catalyst. But if the activation energy is high, that is when we need a catalyst. That is when it will be slow without a catalyst. And when I add a catalyst, we said a catalyst lowers the activation energy, so my reaction would be fast. Okay? The cell diagram for an electrochemical cell is shown. You know how to write a cell diagram? So this represents what? It represents the fact that I have an platinum electrode, and it is in a solution of iron 2 plus in equilibrium with iron 3 plus. So I have iron 2 plus going to iron 3 plus. So that is my oxidation. And then on the other cell and other part of the cell is bromine going to 2Br minus. So that is the reduction. And then another platinum. So that is called the cell diagram for the electrochemical cell. And he's telling me that the overall E cell is plus 0.32 volts. What are the half equations for the reactions that occur? So looking at what he wrote, I should have on the left hand side something that says iron 2 going to iron 3 plus. So my answer should be A or B. And then in the right hand half cell, I should have Br2 going to 2Br minus. And that means that it should be B. And that is because if I have iron 3, what you look at the data booklet, it will tell you the Fe3 plus E electron to Fe2 plus is plus 0.77. But what we are dealing with is the other way around. Remember that when we invert the equation, we also invert the sign. So for the Fe2 plus going to Fe3 plus, the E of that half cell is minus 0.77. Now, looking again at the data booklets, we'll find Br2 plus 2 electron to give Br minus, it's plus 1.09. So that is the voltage for that cell. And if you calculate the overall 1.09 minus 0.77, this will give you the overall E cell of plus 0.32. The others will be wrong. For example, A is giving two half equations. Both of them are oxidation. You can't have both of them oxidation. D, for example, gives you two. Both of them are reduction. You can't. One of them has to be oxidation. The other has to be reduction. And if you look at C, C is the wrong way around. We don't have 2Br minus going to Br2. We have the other way around. Okay, so the answer for that would be B. Okay, what is the minimum volume in centimeter cubed of oxygen needed for the complete combustion of a mixture of 50 centimeter cube propene and 50 centimeter cube butane gases? So if I write the equation for combustion, and this is complete combustion, so this gives carbon dioxide plus water, the equation for propene tells me that if I have 1 mole of propene, it needs 4.5 moles of oxygen. And that means 50. Remember that these relationships apply to moles and they apply to volumes of gases. So if I say I have 50 centimeter cubed of propene, then I need 50 times 4.5 of oxygen. So I need 225 centimeter cubed of oxygen for propene. Now, butane, also I write the equation balance. I find that 1 mole of butane needs 6 moles of oxygen. So that means 50 of butane will need 50 times 6, which is 300. So if I have a mixture of these, then I have the total oxygen needed is 525 centimeter cubed. A sample of air contains 405 parts per million of carbon dioxide. What is the approximate volume of carbon dioxide in 250 of this air? You know that if I have parts per million, this is the part of the carbon dioxide over the total times 10 to the 6. That's what we mean by parts per million. So he's telling me that it is 405 parts per million. We don't know how much of carbon dioxide over the total times 10 to the 6. So you can solve for x. That comes out to be 0.1. So we need 0.1 centimeter cubed of carbon dioxide. This question is about the infrared and proton NMR of amino acid valine. Which of these wave number ranges would you not expect to have an absorption in the IR spectrum of valine? So which of these would not apply to this molecule? Now, he's saying a peak at 3500 to 3300. Well, that's the peak for NH, and I do have NH in this molecule, so I would expect to have that in the IR. Now, 3095 to 3010, well, if you look at the data booklet, you will find that the CH stretch for alkane is 2962 to 2853. So that is what I have in C. I can have that, but the 3095 to 3010, this is for alkenes, and I don't have alkenes. So this is the one that I would not get. But I would have the one for the CH for alkanes because I do have CH of alkanes there. And I would expect the 1725 to 1700 because that is for the C double bond O in the acid. So my answer here would be B. What are the expected splitting patterns in the high-resolution proton NMR spectrum of valine? So this is valine. Now, he wants the splitting pattern for CH3 protons. Where are the CH3 protons? These are the CH3 protons, and the CH3 protons have only one hydrogen on the neighboring carbon. And that means, remember that the splitting pattern follows an n+1 rule. So if I have only one hydrogen, then I will have a doublet for that splitting pattern for CH3. So the CH3 is a doublet. So my answer is A or B. Now the splitting pattern for the CH, that's that H down there. If I look at the carbons nearby, I have many hydrogens. I have CH3 and CH3, and the neighboring carbon has an H, and that means that I have a total of what? Of 7 hydrogens. So according to the n+1 rule, that would be an octet. Okay? Grignard reagents are used to increase the length of the carbon chain in organic molecules. What type of reaction occurs with a Grignard reagent? Do you remember what's a Grignard reagent? This is something with MgBr or MgCl, and we said this acts as a nucleophile that attacks a carbonyl. So this would attack the carbonyl of a ketone, for example, to form an alcohol in the end, and that attaches new chains or new carbon atoms to the carbonyl group. So this is an example of a nucleophilic addition. Please remember the Grignard reagent and how it works. Benzaldehyde reacts with a Grignard reagent followed by hydrolysis to form this compound 2-methyl-1-phenylbutane-1-ol. What is the formula of the Grignard reagent that I need to react with that aldehyde? So I have that benzene ring with an aldehyde group, and I am reacting it so that I have that part is what I got from the benzene and the aldehyde group. So the rest is what I got from the Grignard. So that means that my Grignard reagent will be that chain with an MGBR. So which one does that apply to? Which is my answer? So if you look at B, you will find that that is the correct chain that we need to add to the carbonyl of the aldehyde. A student hydrolyzed a section of a protein and then used thin layer chromatography to analyze the amino acids produced, and the chromatogram is shown. What is the best estimate of the RF value of the amino acid labeled X? So can you see X? What do you think would be the RF value of X? You should know that when we want to know RF values, it is the distance from baseline to the spot over the distance from baseline to the solvent front. So in this case, my RF value is what we measure at X over what we measure at Y. Now, looking at it, what do you think the answer would be without even measuring? You should notice that the spot we're looking at, which is X, is above half of the chromatogram. So estimating it, that would be 0.6. It's not 0.8. 0.8 would be the one that is nearer to the solvent front, and it's not 0.2. 2.2 would be the one that is nearer to the baseline. So if the spot is above half of the chromatogram, so it's probably the RF value would be about 0.6. A polyamide has this repeat unit. Which of these monomers can form this polyamide? Well, when he gives me the polyamide, I look at it and I break it up. This was made of, the part on the left was the diacid or the diacid chloride, acyl chloride, and the one on the right would be the diamine. So if I'm looking for the monomers, the one on the left would be a monomer like this. The one on the right would be this kind of monomer. So which one is my answer? So my answer is D. Can you see how we do it? You break it up and decide which part is which monomer. A reaction scheme for the preparation of an azo dye from phenylamine is shown. What are the reagents and conditions for step 1? In step 1, you're changing the amine to a diazonium salt. And you should know that the conditions for this is when we try to change the NH2 to a diazonium salt, we add sodium nitrite, NaNO2, HCl at a low temperature, not at a high temperature. We don't use 50, for example, because that would break up the diazonium salt. Which reagent and conditions are used for step 2? Which one was step 2? Can you see step 2? We're trying to react the diazonium salts with something in order to get this overall compound. So the other reagent would be that part with 2 benzene rings, and notice the position of the OH. So the position of the OH, and we should know that this kind of reaction is in alkaline solution, so this would be my reagent. The others, C and D, have the OH in the wrong position, and A is acidic. We don't do this in acidic, we do it in alkaline conditions. The organic compound for aminophenol can behave as an acid and a base. That's the one on the right. What is formed when this compound reacts with acid? You should remember, if I have an amine and you add acid, then the amine becomes NH3+. So that is the compound formed when you add acid to something that has an amine. Organic compounds can be analyzed using a combination of qualitative analysis, quantitative analysis, and spectroscopic techniques. An organic compound A contains carbon, hydrogen, and oxygen only, has a molar mass of 136, complete combustion of 5.26 grams of A in dry oxygen gives this amount of carbon dioxide and this amount of water. Show that the formula is C9H12O. Okay, so we're basically trying to get the empirical formula of A. So what should we do? He gives me a mass of carbon dioxide. I can get number of moles of carbon dioxide, that's mass over molecular mass, and that gives me a certain number of moles, and you know that the carbon dioxide has 1 mole of carbon in it, so the number of moles of carbon dioxide is the same as the number of moles of carbon. So now we have number of moles of carbon. I can get the mass of carbon, number of moles times mR. So that means I have about 4.17 grams of carbon. Now we do the same for water. We have number of moles of water is mass over molecular mass. So that gives me number of moles of water, but each mole of water has 2 moles of hydrogen. So the number of moles of hydrogen is the moles of water times 2. And that means I can get the mass of hydrogen, and this is 0.46. Now I can get the mass of oxygen. We subtract both of these from the total mass. So the mass of oxygen, we started with a total mass of 5.26 minus mass of hydrogen plus mass of carbon, and this gives me the mass of oxygen. So now I have number of moles of oxygen. Number of moles would be the mass over the atomic mass. So that gives me number of moles of oxygen. I have now number of moles of carbon, number of moles of hydrogen, number of moles of oxygen. I can divide by the smallest to simplify the ratios, and that ends up with C9H12O. Compound A, the one we were just talking about, contains a benzene ring and 1 side chain. Now, A is oxidized when heated with acidified potassium dichromate, and that means that A is either a primary or a secondary alcohol. To produce a compound B that reacts with iodine and aqueous sodium hydroxide to give a pale yellow solid. Now, what gives a yellow precipitate with iodine in aqueous sodium hydroxide? That is something that has a CH3 C double bond O group. So if we look at this, he's saying that A is oxidized to form B, and B must be something that has a CH3 next to the C double bond O, so that when I react it with iodine in sodium hydroxide, then it gives me the yellow precipitate of CHI3. Then he says, when A reacts with concentrated phosphoric acid, it forms a mixture of 2 structural isomers that decolorize bromine water. So you should know that concentrated phosphoric acid would remove water and form a double bond. So that is why D and E would decolorize bromine water, and he's telling me that D would have a geometric isomers, but E would not. So that means that when we added the acid, we formed a double bond. So D is the one that can have geometric isomers, E or Z, and D will not have geometric isomers, so that means that the double bond in E is at the end of the chain. Can you see how we obtain the structures? Compound F is a structural isomer of A, which also has a benzene ring and 1 side chain. Structural isomer of A, that means it has the same molecular formula. So we're still looking at something that has C9H12O, and he's telling me it still has a benzene ring, but then F is not oxidized with potassium dichromate. That tells me that it must be a tertiary alcohol. Remember that tertiary alcohols are not oxidized with potassium dichromate, And he's saying the carbon-13 NMR has 6 peaks. So what would the structure of this look like? This is a possible structure for it that complies with all the rules. So he's telling me it's not oxidized, so it's a tertiary alcohol, and it will have 6 peaks. Can you see the 6 peaks for the carbon-13 NMR? How many carbon environments do I have? I have the carbons of the CH3, so that's 1. And then the carbon that has the OH, and then the carbon that binds that to the benzene ring, and then the benzene ring is symmetrical here. So we have only a total of 6 different carbon environments. Can you see that? Oh. Compound G is a structural isomer of A, which also has a benzene ring and one side chain, but he's telling me that the mass spectrum has a peak of 107. So we need to draw a structure that has part of it giving a peak at 107. So what kind of structure? Let's take a look at this structure. Would this give me a peak at 107? Yes, if you calculate the MR of that, that is the C7H7O plus. So that would give a peak at 107. And it still has the same, he's saying it's a structural isomer, so it still has the same molecular formula as the others. Vanadium forms compounds with oxidation states +2, +3, +4, +5. What is the oxidation number of vanadium in this compound? So I have this compound Na3VO4. How do we determine the oxidation number of vanadium? You know that sodium is in group 1. So each sodium has +1. So I have 3 sodiums, that's +3. Plus, let's say X for vanadium. We don't know what is vanadium. You know that each oxygen is -2, so that's -2 times 4. And the overall, there is no charge, so overall it should be 0, and you just solve for X. So X comes out to be +5. So this is vanadium +5. In aqueous solution, vanadium-2 exists as V with 6 water around it, but vanadium-5 exists as VO2 with H2O4 around it. Explain why vanadium-5 does not exist as V with 6 water around it. So he's telling me if it is vanadium-2, vanadium-2 plus would look like this. Vanadium-2 plus has 6 water molecules complex to it. But if I have vanadium-5, I cannot put 6 water around it because vanadium is a small ion with a high charge density. So it will polarize 2 water molecules, weaken the OH bonds, causing them to lose H plus ions. So you don't have 6 water, you have only 4 water around. Hydrated potassium vanadium sulfate contains this percent potassium, percent vanadium, percent sulfur, percent hydrogen, and percent oxygen. Calculate the empirical formula of this compound and hence write the overall formula showing the potassium vanadium sulfate ions and the water of crystallization. Okay, so let's use these percentages to get the empirical formula. We divide first by the atomic mass of each one, and then we look at these numbers, divide by the smallest, and we get this kind of ratio, 1 to 1 to 2 to 24 to 20. And that means this is the formula. But he's telling me that it is potassium vanadium sulfate with water. So potassium vanadium sulfate, that means potassium and vanadium is 3, potassium is 1, and that means I have a total of +4. That means I need 2 sulfates to have -4. And that means the rest of the hydrogen and the oxygen are the water of crystallization. So that means I have 12 water of crystallization. So that would be the formula of the hydrated salt. An acidified aqueous solution of potassium manganate 7 oxidizes vanadium 3 ions. In an experiment, 10 centimeter cube portions of a solution containing 0.132 mole per decimeter cubed vanadium 3 ions are titrated against 0.02 mole per decimeter cubed of potassium manganate in acidic conditions. And the mean titer is this. Calculate the ratio of the number of moles of manganate ions to the number of moles of vanadium 3 ions. So basically we want to get number of moles of each. So what is the number of moles of V3 plus ions? Concentration times volume. I have a concentration of 0.132 and the volume is 10 centimeter cubed. So that's 0.01 decimeter cubed. And this gives me the number of moles of V3 plus. Now, doing the same for the manganate, the concentration is 0.02 and the volume is 26.4 centimeter cubed. So you divide that by 1,000. That gives the number of moles of manganate ions. What would be the ratio between these? We divide by the smallest, and that gives me a ratio of 1 to 2.5 or a ratio of 2 to 5. Write the equation now for the reaction between the manganate ions and the vanadium ions. We said it's a ratio of 2 to 5, so this is 2 manganate plus 5 V3 plus, and then you should realize that this will react with water to give manganese 2 plus the vanadium VO2 plus 4H plus. Okay, so this is the balanced equation for the acidic solution. Vanadium ions in acidic solution may be reduced step by step through its oxidation states. Compare and contrast the use of iron and tin in this reduction process. So he's trying to reduce vanadium ions step by step through its oxidation states using iron and using tin. Include equations and denote cell values for any reactions. State symbols are not required. Use only data from these tables. So he gives me the data and he's telling me find out as we go along from the vanadium oxidation states which ones will reduce the vanadium and which one will not. So if we are talking about reducing vanadium plus 5 to vanadium plus 4, we look at the information he gives me. This is the equation for vanadium plus 5 to vanadium plus 4. And then we have the equation for the iron, but you should realize that we're not using that equation, we're using the inverse of it. So I want iron going to iron 2 plus. And remember that when we invert the equation, we invert the sign. So that lower equation is iron going to iron 2 plus. So now it's a plus 0.44. Then I need, in order to add the two half equations, I need to multiply the upper equation by 2 in order to be able to cancel the electrons. I want 2 electrons each. So we multiply through by 2, cancel the electrons, add up everything on the left and everything on the right. So this is the net equation for the reaction. The E cell for that will be the plus 1 plus 0.44, and that means the E cell for this is a positive value, and that means iron will reduce V plus 5 to V plus 4. Now, if we look at tin, we also have this equation, and we have the equation for tin 2 plus to tin. So I need to invert that lower equation, and that means invert the sign. Multiply the upper equation by 2 so that I can cancel the electrons, add up everything on the left and everything on the right, so that is the net equation, and add up the E's for the cells, and that comes out to a positive value, and that means both tin and iron will reduce vanadium plus 5 to vanadium plus 4. Now, going down from plus 4 to plus 3, we look at the same equation from plus 4 to plus 3. And the one for iron, we're going to invert. And we're going to multiply the upper one by 2 also, add them all up. So this gives me the net equation, and add the E cells, and that gives a positive value, and that means that iron will reduce V plus 4 to V plus 3. Now for tin, again, this is the equation for V plus 4 to V plus 3. The equation for tin, I need to invert and therefore invert the sign. So it becomes plus. I multiply the upper equation by 2 in order to cancel the electrons. Add up everything on the left, everything on the right. Add up the E of the cell. This comes out to be a positive sign, and that means also that both iron and tin will reduce V plus 4 to V plus 3. Now, going from V plus 3 to V plus 2. This is the equation for V plus 3 going to V plus 2. I need to invert the equation for the iron and invert its sign. Multiply the equation on top by 2. Cancel the electrons. Add up everything on the left, everything on the right. What is the E cell total? A positive. That means iron will reduce the V3 plus to V2 plus. Now, doing the same thing for the tin. This is the V3 plus to V2 plus. This is the equation for the tin, but I need to invert it. That means invert the sign, multiply the equation on top by 2 so that I can cancel the electrons, add up everything, and that means the E cell is, in this case, a negative number, and that means tin will not reduce the V3 plus to V2 plus. Do we understand how to decide whether something works or not? Okay. This question is about some organic nitrogen compounds. Phenol reacts with dilute nitric acid at room temperature to form a mixture of 2 nitrophenol and 4 nitrophenol. So he's saying phenol reacts with dilute nitric acid. It can form 2 nitrophenol and 4 nitrophenol. The reaction is electrophilic substitution. Draw a mechanism for the reaction to form 2 nitrophenol and assume that NO2 plus is the electrophile. So how does this kind of reaction work? You should realize that when I have the benzene ring has high electron density. It will attack the NO2 plus, and that means I need to lose the hydrogen in order to remove the positive sign in the benzene ring, and that gives me my product. You should be able to draw this mechanism. Benzene requires a mixture of concentrated nitric acid and concentrated sulfuric acid at 60 degrees Celsius to form nitrobenzene. So it needs strong conditions to form. Explain why phenol requires milder conditions for nitration. It's easier for phenol to react than benzene. So we say that phenol reacts easily in milder conditions than benzene because of the presence of the OH, the electrons, the lone pair of electrons on the oxygen overlaps with the delocalized electrons in the pi cloud of the benzene ring. So you have spreading of the electrons all over the benzene ring. This increases the electron density of the ring. Devise a synthesis of N-phenyl ethyl ethanamide, so that's that compound on the right, from bromomethylbenzene, that's the compound on the left, and he's saying without using Grignard. So we don't want to use Grignard reagent. Include reagents, conditions, and structures of the intermediate compounds. So if I'm starting with that bromo methyl benzene, how do I change it to this compound? You realize that we need to increase the number of carbons in the ring. We need to react so that we add that NH double bond O part. So how do we do that? We can react the bromobenzene with potassium cyanide in aqueous ethanol. This will add a cyanide group, and remember, this is the method of adding an extra carbon atom to the chain. So this gives the cyanide molecule. I can then reduce that using lithium aluminum hydride dry ether, then dilute HCl. That will give me the amine. Now I can change this amine to that compound on top by adding ethanoyl chloride. That would give me that final compound. Phenylalanine is a naturally occurring amino acid found in meat, milk, and eggs. It is used to form the artificial sweetener known as aspartame. Complete the structure of this Zwitter ion of phenylalanine. Remember, amino acids can form Zwitter ions. What does that mean? That means that the OH donates its H plus to the ammonia, so I end up with NH3 plus and O minus. This is called the Zwitter ion of an amino acid. Draw the structure of the dipeptide formed from phenylalanine. This was phenylalanine. Now, a dipeptide means two of them joined together. And when we join two amino acids together, it is one amine from one joining with the acid of the other. So I will have something like this, in which the amine of one of them attacks the acid part of the other, so that we form an amide linkage. Give the molecular formula of aspartame. He already gives me that this is the formula of aspartame. What is the molecular formula? Well, let's take a look. You need to take a look at all the carbons, all the hydrogens, all the nitrogens, and decide what is the formula. You will find that it is C14H18N2O5. Please do not make any mistakes in the hydrogens in these molecules. Circle the two chiral carbon atoms. What's a chiral carbon atom? It's a carbon atom that is attached to four different groups. Where do we have that? We have in these two carbons, each of them is attached to four different groups. Can you see that? There is a hydrogen plus the NH2 plus the rest of the chain. So each of these is a chiral center. Aspartame is hydrolyzed by hydrochloric acid in the stomach. Draw the structures of the three organic products formed from complete hydrolysis of aspartame. This was aspartame. So if we hydrolyze this, we hydrolyze the amide linkage and the ester linkage that is down there. So we end up with this part from the one on the left, this part from the one on the right, and this is the part that was the ester. Okay? A can of fizzy drink contains 53 milligram of aspartame per 100 centimeter cubed of drink. Calculate the number of molecules of aspartame in a 330 centimeter cubed can of the drink. Okay, how do we calculate number of molecules? We need to get number of moles first. We need to get, if he's saying, first of all, he's saying 53 milligrams in 100 centimeter cubed of drink. He wants how much in 330. So this will give me the mass in 330, But this is mass in milligrams, so I need to divide by 1,000 to get it in grams. Then I can get the number of moles. So the number of moles would be the mass over the molecular mass. So this is the number of moles of the aspartame in 330 centimeter cubed of can, but he wants number of molecules. How do we get number of molecules? It is the number of moles times the Avogadro constant, and that gives me the number of molecules that is required. Manganese and some of its compounds. Manganese is the 12th most abundant element in the Earth's crust, and it is an essential element for all living organisms. Manganese is a transition metal. It can form compounds with oxidation states from +2 to +7. Although not all these are stable, and some readily undergo disproportionation. Some compounds and ions containing manganese are effective heterogeneous and homogeneous catalysts. Alkaline batteries have manganese 4 oxide cathode and are used in digital cameras and toys. They have a similar voltage to the traditional zinc-carbon batteries, but have a higher energy density and last longer. Anyway, the question says some of the properties of manganese and its compounds depend on electronic configuration. So complete the electronic configurations for a manganese atom and a manganese ion. If you look at the periodic table, you would realize that the manganese has 3d5 4s2. So when it forms a 2+ ion, remember it is the electrons in the 4s that are removed. So we end up with an ion that is half filled within the 3d sublevel. The standard electrode potentials for the half cells involving oxidation states +3, +2 for manganese and iron are shown. Explain in terms of electronic configurations why the E0 value for the Mn2+ to Mn3+ is significantly higher than that of iron 2+ to iron 3+. Well, let us take a look. If we're looking at manganese 2+, manganese 2+ is a stable ion because it has a half-filled 3d sublevel. Now, if I'm trying to get Mn3+, Mn3+ is not stable. It has lost one of its electrons from the 3d, and that means the Mn2+ is more stable. So, Mn2+ has half-filled d sublevel. It is more stable than manganese 3+. Now, if we're looking at the iron 2+ and the iron 3+, the iron 2+ has 6 electrons in its 3d sublevel. Now, if it loses that 6th electron, it becomes a half-filled 3d sublevel. So actually, the iron 3+ is more stable, or the iron 2+ is less stable than the half-filled d sublevel in the iron 3, and that is why the iron 3 to iron 2+ has a much lower E0 value. Manganese oxide is an oxidizing agent and a catalyst. Chlorine can be prepared in a laboratory by reacting manganese oxide with concentrated hydrochloric acid. Explain in terms of oxidation numbers why this is a redox. Okay, what's happening to the manganese? The manganese is changing from +4 to +2, so that is reduction. The chlorine is changing from -1 to 0, so that is oxidation. So this is a redox reaction. Remember, when you explain why something is a redox, you need to indicate which one has been reduced and why, and which one has been oxidized and why. Manganese oxide catalyzes the decomposition of hydrogen peroxide. 100 centimeter cubed of a solution of hydrogen peroxide decomposed to produce 86 centimeter cubed of oxygen gas, measured at room temperature and pressure. calculate the concentration of hydrogen peroxide solution. So, what does he give me? We have 86 centimeter cubed of oxygen, so I can get number of moles of oxygen gas, so that's volume over 24, and of course the volume has to be in decimeter cubed. Then I can get from the equation that the number of moles of H2O2 would be twice that of oxygen, so I get number of moles of H2O2. Now, that means the concentration would be the number of moles over the volume, which is 100 centimeter cubed or 0.1 decimeter cubed. So this is the concentration of hydrogen peroxide in mole per decimeter cubed. Potassium manganate is a green solid. In acidic solution, the manganate 6 ions disproportionate to form manganate 7 ions and manganese 4 oxide. Write the ionic equation for this disproportionation. So potassium manganate, that is, I want the ionic, so the potassiums will cancel on both sides. And we have the MnO4 2 minus plus H plus, because he's saying this is acidic solution, and he's telling me that this will give the manganate 7 ions, so that's MnO4 minus, and manganese 4 oxide, that is MnO2, and that means I will need water on the right to balance the hydrogen on the left, and this would be the balanced equation. Remember, this is a disproportionation reaction. What does that mean? It means that the manganese changed from +6 to +7 in one case, and from +6 to +4 in another case, and that means the same species was once oxidized and once reduced. Manganate ions react with ethane diowate ions in acidic solution, and he gives me the equation. And he says 2 experiments were carried out. Aqueous potassium manganate was added to a mixture of excess ethane dioic acid and sulfuric acid. The concentration of the manganate ions was determined as the reaction progressed. The same volumes and concentrations of solutions as in experiment 1 were used, but some solid manganese 2 sulfate was dissolved in the ethane dioic acid. So remember that in experiment 1, when he reacted it, it gave manganese 2 plus. In experiment 2, he started by adding to the reaction, he added a manganese 2 plus. Graphs of the concentrations of the manganate ions against time are shown, and he's saying explain in terms of catalysis why the graphs have different shapes. Okay, so what was he saying? He said experiment 1, we have a reaction of manganate to give Mn2 plus in the reaction, but in experiment 2, he started by adding to the mixture manganese 2 plus. So obviously when he added manganese 2 plus, it made the reaction faster, and that means that the reaction is catalyzed by manganese 2 plus ions. So the reaction experiment 1 starts slowly. We don't have manganese 2 plus at the beginning, but it speeds up as the manganese 2 plus ions are formed. In reaction 2, the reaction is fastest at the beginning because we already have manganese 2 plus. Methyl benzene is oxidized to benzoic acid by heating under reflux with an alkaline solution of potassium manganate. In an experiment, 1.73 grams of methyl benzene was mixed with 7 grams of potassium manganate and excess potassium hydroxide solution, and he gives me the overall equation. Show that potassium manganate is in excess. Now, when he says I need to show that something is in excess, that just means I need to calculate the number of moles of each. So, what do we have? Number of moles of methyl benzene is the mass over the molecular mass. So that comes out to this number of moles. What about the other one? The number of moles of potassium manganate is mass over molecular mass, and that gives me the number of moles. Now I go back to the equation and I take a look at the mole ratio of the methyl benzene to the permanganate. Now what happens is the number of moles of manganate that we need is twice that of methyl benzene. So actually we needed only 0.0376, and he put more than needed, so that is why we're saying that the manganate is in excess. State how the benzoate ions can be converted into benzoic acid. Of course, if I have benzoate ions, in order to make it acidic, I just add an acid like dilute hydrochloric acid, for example. That would put an H plus on the ion. Alkaline batteries consist of an anode made of a zinc alloy, a cathode made of manganese oxide, and an electrolyte of aqueous potassium hydroxide. And this is the overall equation. And he's saying write the half equations for the reactions at the anode and the cathode. Of course, the anode, that is where we have the oxidation. So that is the zinc to zinc oxide. And we need, this is alkaline solution. So we have an OH minus, and we need to balance that with water on the other side. We have two negative charges before the arrow, so we need 2 electrons after the arrow. Now the cathode, this is where the reduction happens. So this is where we're going to have the amino 2 plus changing to MN2O3, and this would be the balanced equation. The standard electrode potential for the zinc oxide half cell is minus 1.28. Calculate the standard electrode potential for the MnO2, Mn2O3. So we have this overall equation. So the overall E cell is the E of each of them, and that means that the E of the manganese MnO2, Mn2O3 half cell would be plus 0.15 volts. And that's the end of this paper. I hope this was useful, and please share, like, and keep listening to the videos. Thank you.